All right, so to find this derivative, we got to basically do a little bit of planning. We got to start by identifying what kind of rules are we actually going to need here. So we were just doing chain rule. So we got that, we got quotient rule, we got product rule, and of course some of the basics like power rule as well.
Oh, you got the theta rule.
So I see e to the theta, and then the parentheses. Is this a function within a function here?
No.
Yeah.
Well,
It should be product rule.
This right here, this tan theta minus theta,
It's just multiplied.
it looks like it's just being multiplied by e to the theta. Because this is going to be e to the theta times tan theta minus theta. So, since it's multiplying, product rule. Alright, so then let's go ahead and apply the product rule here. So that's going to be g prime of theta. Now, it's got theta in here. What's that change?
Nothing.
Nothing.
It's like
yeah.
an X, right?
Yeah, it works just like x. It's just a different letter. It's just the Greek letter theta. But hey, mathematicians love Greek letters, so you got to be able to do the same thing with those. So for product rule, we do original times derivative. And so that's going to be e to the theta times the derivative of tan theta minus theta. All right, so what's the derivative of tan theta? Yep.
Minus 1.
Secant squared of theta. Then minus the derivative of theta, which is 1. Then that's going to be plus derivative times original. Well, the derivative of e to the theta is e to the theta. And it's times original, so the tan theta minus theta stays exactly as it was. And so then that's technically done. In terms of a few little variations that you might see, though, just because I want you aware that this can be written the same way, oftentimes we look at how do we simplify it or rewrite a different way. Since both of these include e to the theta, we can factor that e to the theta out. And if you do so, it'd be secant squared of theta minus 1 plus tan theta minus theta, all in one set of parentheses there. All right, for this problem, we're finding the derivative. Now, you got a couple different options about how you can do it. Option 1, we can look at this as cosine of theta squared, because remember that's equivalent, times sine of theta squared. And then I see a chain rule situation, so we could use chain rule then to find the derivative of each of those, where the inner function is sine or cosine, the outer function is that it's squared. Or, at the very start of the problem, we can recognize that cosine squared plus sine squared always equals the same thing. What does cosine squared plus sine squared always equal?
1. Very true.
And therefore, y equals 1. And if y equals 1, then y prime equals 0. Because remember, the derivative of any constant, if it's just a constant, is 0. So for this problem, the first thing you're having to do is think about what rule to use. We have cosine theta, sine theta. Notice this is cosine theta times sine theta, therefore product rule. So you should be using product rule as you're finding this derivative. So to find our derivative here, since it's product rule, that's original times derivative, so it's going to be cosine of theta times the derivative of sine, which is cosine of theta, plus derivative of cosine this time, which is going to be negative sine of theta, times sine theta. And so we can go ahead and clean this up then. So we end up with cosine squared of theta minus sine squared of theta. All right. What does cosine squared of theta minus sine squared of theta equal?
Negative 1.
Nothing.
No, it just equals cosine squared theta minus sine squared theta. It doesn't reduce. That is not an identity. And so this is actually as good as our answer can get. All right. So first thing we got to decide when taking a look at this equation, find its derivative, is thinking ahead to what rules will we need to use. And there's two terms, so we'll have to see what rules we use for each term individually. For this first term, is this sine times E of t, or is it sine of E of t? Yep, it's of.
I know areas.
If it were going to be times, it'd be like sine t parentheses E of t, or something like that. So because that E of t is actually in the function of sine, that's going to be chain rule. And in that case, the inner function is going to be the e to the t. All right, for the second part, e to the power of sine t. Notice that's e to the power of something other than just our variable. That means that the sine of t has been plugged into that function of e to the power of x or e to the power of t. And so this is also going to be chain rule. Which means that the sine of t in that case will be the inner function. So basically we have the same two functions being used in each one, just the order about which one is being plugged into which is changing. So now go ahead and use chain rule, find the derivative on each to see how that changes your answer. So to find our derivative then, f prime of t is going to equal, so for chain rule, it is derivative of the outer function, so derivative of sine is cosine, so it's going to be cosine of the same thing, so cosine of e of t, times the derivative of the inner function, so that's going to be times the derivative of e of t, which is just e to the t. Alright, then the plus. And of course, it's a plus in between them just because the original has a plus in between them. We're just carrying that through. Now we do derivative of the outer function, which is e to the power of sine t, times the derivative of the inner function. The inner function here is sine, so that's going to be times the derivative of sine, which is cosine. And so there's our derivative. And notice here, one of the differences is that in the first parentheses, the e of t is inside the cosine, and in the second one, it's only t that's in the cosine. And yes, it's optional if you put the parentheses around the t and the cosine there. Now with this one, first of all, if you really wanted to, you could actually multiply it all out. But do you really want to be doing that? No.
I don't.
That's way harder. So, what I see going on here is I got parentheses cubed times parentheses to the 6. Since they're multiplying, I know that I'm going to have product rule happening. So we're going to be using product rule, and then we use product rule, and we find the derivative of this. Well, notice that's a function within a function again. The x squared plus 1 is the inner function, and it being cubed is the outer function.
What?
And so for that part, we're going to have to use chain rule. And what about this last part when we find the derivative of that?
Also chain.
Also chain rule. And so this one's going to involve the product rule and the chain rule. So go ahead and find that derivative. All right, so in doing this one, we got to start by using the product rule. So product rule says original times derivative. So the original, the first one, it just stays the same. And then times the derivative. Now the derivative of this, that's where we now have to use the chain rule. So within product rule, we're having to now use chain rule. So the derivative of that is going to be 6 times the x squared plus 2. Now to the 5th power times the derivative of the inner function, which is 2x.
Shut up. Never say that to me again.
All right, then we do derivative times original. And so that's going to be then chain rule for that first derivative. So 3 times x squared plus 1 squared times the derivative of the inner, which happens to also be 2x, times the last function, which is x squared plus 2 to the 6. So we're still using product rule. It's original times derivative plus derivative times original. It's just that when we find those derivatives within there, we have to use the chain rule.
That's a long.
Now, little side note here. Yes, we could do some cleanup here. I'm not going to worry about doing it right now, but we could do things like writing the 6 and the 2x first, so it ends up being like 12x, and then the parentheses and so on. So you can do some cleanup here, but again, you don't have to do it. But some people were asking, so I want to say that we could. So first up, the planning phase. So what rules will we have to use? Well, you'll notice that we have the e to the negative 2t times cosine of 4t. So that already tells me it's product rule. Then, the two that I'm multiplying together are these functions. Now for that first part, the e to the power of negative 2t, will I need chain rule for that? Yes. If it were just e to the t, we wouldn't. But if it's anything other than a t in the exponent, we need chain rule there. And then for cosine of 4t, will we need chain rule for that one?
Yes.
Yes. Because again, if it's anything other than just the variable inside of it, you need chain rule. So the 4t is what we need to use chain rule with. 4t will be our inner function. So we know we have to use product rule here.
We got it.
And so we do original times derivative, so that e to the negative 2t just stays the same in this first one. Now I'm going to be multiplying that by the derivative of cosine of 4t. So I do derivative of the outer function, which is going to be negative sine. And remember that whatever is inside, it stays inside when we do that derivative of the outer function. But then I need to multiply it by the derivative of the inner function. And the derivative of 4t, of course, is just 4. And so there's our first part. I now need to add, because this is product rule, and do derivative times original. So now I'm going to do the derivative of the e to the negative 2t. So that'll be e to the negative 2t still, but times the derivative of negative 2t, which is negative 2.
Jinx, you miss me.
And then times the original, so times the cosine of 4t, just like it gets left.
Got it. Literally. Boom.
And then that's our final answer. So for this one, figuring out which rules we need to use is probably easier. Because obviously there's a big old fraction in there, right? And so for that reason, yes, you're going to have quotient rule, but notice that that fraction is inside of the square root function. And so that's going to be chain rule. And so you're going to be using both chain rule and the quotient rule in doing this one. All right, now first up, when you approach one of these that has a square root, of course that's the same as the 1/2 power. Write it that way at the start to make your life a lot easier. Then we can go ahead and start taking our derivative. So f prime of s here is going to equal, now in this case the chain rule is the first thing we encounter because I have to do the square root of a function. So let's go ahead and use the power rule on the 1/2 power. And so that's going to give me 1/2 times, of the same stuff to the power of negative 1/2. Now that same stuff is always on the inside, so I just keep it as s squared plus 1.
Oh, wait, what?
Over s squared plus 4. So that's the outer part of the chain rule. But now I need to do the derivative of the inner function. The derivative of the inner function, though, that's where we need the quotient rule. So we're going to do low d high, so that's s squared plus 4 times the derivative of the top, which is 2s, minus high d low, so the top s squared plus 1 times the derivative of the bottom, which is another 2s, all over the square of what's below, so that's going to be over the s squared plus 4 squared.
And that's it.
And no, we don't have to simplify it. We can go ahead and leave it just like this.